Web3 login starts when a browser app asks a wallet for permission. The wallet provider becomes the bridge between JavaScript and the user's blockchain identity, allowing the app to read accounts and request signatures without ever handling a password. You already have the building blocks: blockchains, web authentication, public key identity, wallets, seed phrases, and message signing. Now we'll connect them inside real browser dApps where wallet interactions become a practical login flow. A dApp is not a completely new kind of software. It often starts like a normal web app, with HTML, JavaScript, React, APIs, and familiar browser interfaces. What changes is what it can connect to. Instead of relying only on a private server or database, it can read from and write to smart contracts. The user's wallet signs actions, proves ownership, and bridges the app into the blockchain layer. A dApp separates what the user sees from what controls value. The front end renders the experience and prepares requests, but it should never hold private keys. When the app needs an account connection, message signature, or transaction, it asks the wallet. The wallet shows the user what is being approved, signs locally, and sends data through an RPC provider to read chain state or broadcast transactions. Backend services can still support profiles, metadata, analytics, or other off-chain logic. In many Web3 apps, the wallet becomes the identity layer. Instead of creating a username and password, you choose an account from the wallet and share its public address. The app can use that address as an identifier. When stronger proof is required, the wallet signs a message to show that you control the account. The key boundary remains the same. The private key stays inside the wallet. The application should never receive it, store it, or ask for it. Browser wallets connect to dApps by injecting a provider object into the page's JavaScript environment. In Ethereum-style wallets, that object is commonly window.ethereum. The front-end checks whether the provider exists, then uses it to request accounts, network details, or signatures. The important boundary is user approval. The provider lets the app make requests, but the wallet asks the user before anything sensitive happens. Before calling any wallet method, first check whether a provider is available. In the browser, that usually means confirming window exists, then checking window.ethereum. If it is present, you can enable the connect flow. If it is not, avoid cryptic errors or broken buttons. Show a clear message such as "No wallet detected" and guide the user to install or set up a supported wallet. When the user clicks connect, the dApp asks the wallet for accounts, commonly with eth request accounts. At that point, the wallet becomes the gatekeeper. It shows a consent prompt, and the user can approve or reject the connection. If approved, the dApp receives one or more public addresses for identifying the account and preparing future requests. This still does not expose the private key. Signing and final approval remain under wallet control. In the front end, the connect flow should handle every outcome deliberately. If the wallet exists and the user approves eth request accounts, the provider returns accounts, and the app stores the selected public address in state for display and future calls. If no wallet is installed, the user rejects, or an unexpected error occurs, respond clearly. Also remember, connecting a wallet proves address visibility. It is not the same as server-side authentication. A wallet is not just one identity on one chain. It can hold several accounts, each with its own address, and it can point those accounts at different networks. That combination matters. The same address may show different balances on mainnet, a testnet, or a local chain. A dApp should read both the selected account and the chain ID, so it can confirm the user is interacting with the network the app expects. After connection, the provider becomes the dApp's request channel, but not every request has the same risk. Reading data, such as chain ID, balances, or contract state, is usually low impact. Signing a message proves account control, so the user should understand exactly what they are signing. Sending a transaction is highest risk because it can move assets or change blockchain state. Good dApps explain intent before the wallet prompt appears. Wallet-based login usually starts with the dApp creating a clear message, often including a nonce, so it cannot be reused. The wallet displays that message and asks the user to approve signing it. If approved, the wallet produces a cryptographic signature tied to the user's address. The dApp or server verifies that signature against the public address. This proves control of the wallet without sending a transaction, changing blockchain state, or paying gas. Treat every wallet prompt as a security checkpoint. A connection request shares your public address with the dApp. A signature request proves account control, often for login, so read the message before signing. A transaction request carries the highest risk because it can move assets or change on-chain state. Before approving, verify the site, account, network, fees, and action. If anything looks unexpected or unclear, reject it. A wallet connection is a live relationship, not a one-time setup. Your app should subscribe to events like accounts changed and chain changed, then update state immediately. If the address changes, refresh balances, permissions, and displayed identity. If the network changes, check whether it is supported and guide the user clearly. Rejections and disconnects are normal user choices, not errors to punish. Treat the wallet as a signal of availability and verify authentication separately when needed. You now have the core model. A dApp talks to a browser wallet, asks permission to see accounts, and requests user-approved signatures. The wallet protects private keys while acting as the user's identity and signing agent. Next, we'll turn that connection into a secure sign-in with wallet flow.